Hi, I'm James, and together with my group, we will be presenting the AC generator, also known as the alternating current generator. Through our model, we hope to present to you the concepts, the construction, and the application of the model. Like all other generators, the main aim of the AC generator is to convert mechanical energy into electrical energy. The basic working principle is very much contingent upon Faraday's law of electromagnetic induction, which explains that the wire inside a magnetic field will induce a current when there is a relative motion between that wire and the magnetic field. Hence, we can simply generate an induced current in a coil by either rotating the magnetic field with respect to the coil or rotating the coil with respect to the magnetic field. For our actual model, the reason why we chose to use the former method is due to practical reasons, as rotating the magnet removes the need of slip rings. The Fleming's right-hand rule is a common visual mnemonic, showing the direction of induced current when the magnetic field moves with respect to the wire. The thumb, index finger, and middle finger are all pointing mutually perpendicular to each other. The thumb represents the direction of the force, and the index finger represents the direction of the magnetic field, while the middle finger shows the direction of conventional current flow. On the other hand, Fleming's left-hand rule is applicable for electric motors that convert electrical energy to mechanical energy.
Hi, I'm Justin, and I'll be explaining why an alternating current is produced instead of a direct current. And to do so, we need to understand how current is generated in an AC generator. When exploring the topic of electromagnetic induction, the term magnetic flux will inevitably appear. Also known as magnetic flux density, magnetic flux, put simply, is the amount of magnetic field passing through a surface. Thus, when a magnet rotates, the magnetic field also rotates, resulting in a change in the magnetic flux enclosed by the circuit. And Faraday's law also stated that the magnitude of induced EMF in a closed circuit is directly proportional to the rate of change of magnetic flux enclosed by the circuit. Most current is produced when a wire passes through the magnetic lines of flux at the fastest rate. The greatest current occurs when a wire moves at right angles to the magnetic field. As the wire turns at right angles to the magnetic field is cut by the surface area of the wire itself. The greater the surface area in contact, the greater the current produced. There will be a point in time when the wires moves in a direction parallel to the magnetic flux, and at this point, no current is generated. Alternating current is produced when a wire turns in a direction, causing the magnetic flux to change sinusoidally. The sinusoidal graph causes the current to fluctuate in both directions. Flow of charge that changes direction periodically. Voltage reverses along with the current. To enable an AC generator to produce direct current, or the unidirectional flow of electric charges, a commutator is used. A commutator is a moving part in a generator that reverses the current direction between the wires and the external circuit, so as to achieve a unidirectional current output.
Hi, I'm Bryan, and here are the objects which we use to construct our model.
Some pieces of cardboard, insulated copper wires, a magnet, a chopstick, an electric drill, tape, and a voltmeter. Firstly, we made the structure using cardboard and then manually coiled the copper insulated wires around the 4 planes of cardboard. For the wire ends, we melted the insulation using a flame so that a complete circuit could be formed with the voltmeter. Next, we taped a strong magnet that provided a strong magnetic field to the center of the chopstick, which was then connected to an electric drill. We also ensured that the north-south direction of the magnet is perpendicular to the direction of the wire. As the electric drill rotated the magnet, a rotating magnetic field was produced, intersecting the wires at right angles. This induced an alternating current, which was recorded in the voltmeter. Here is a footage of our model in action, where a voltage of around 0.07 volts measured in AC was generated.
Just remove it. Okay. Remove it.
The alternating current can be seen clearly when the voltmeter was set to DC voltage, as the voltage varied between a positive and negative value.
Hi, I'm Jared, and I'll be presenting on how our simplified model can be improved upon and applied in our daily lives. I will explain the 4 factors in which our model was limited in. 1. The strength of our magnet affects the strength of the magnetic field. Our magnet could have been much stronger and thus would have generated a lot more alternating current. 2. There could have been much more coils of wire, which would have resulted in more wires for the magnetic flux to intersect. 3. The speed at which the magnet was rotated could have been much faster, but this was better than the previous time where we rotated the magnet by hand and did not get any positive result. 4. The area enclosed within the structure we made could have been much smaller and yet able to fit the magnet, because the distance between the magnetic field and the wire should be at a minimum. As seen, these 4 points are factors in determining the magnitude of alternating current. Hence, we bring our attention to the bicycle dynamo, one of the more common items in which the principle behind the AC generator is actualized. The bicycle dynamo is a small generator fitted next to the wheel of the bicycle. When the cyclist rides the bicycle, the wheel rubs against the tire. The small but strong permanent magnet is rotated using the turning motion of the wheel. The rotating magnetic field will then intersect the multiple neat coils of wire at right angles, then generating the fastest rate of change of magnetic flux, which in turn results in the maximum induced alternating current possible.